For this class of Data Communications and Network 1, we will continue with Chapter 10. So it's going to be Chapter 10, Part 2, and also I will begin Chapter 11, Part 1, okay, which is both of them are about local array network, okay, and Chapter 11 is basically based on the Ethernet, okay, so this is Lecture 20 of the class. Okay, now let's talk about the routing with bridge, okay. In general, the bridge has to perform some routing, okay. So when the bridge receives a frame, it has to decide whether to forward the frame and to which of the LANs, okay. If there are more than 2 LANs connected to it, okay. So it's kind of have a node that have to do some of the stuff that can have to do like kind of switching or routing, okay. So if we look at this, suppose we have the network like this, okay? So you have LAN A, B, C, D, E, F, and G, and there are stations connected to all of the LAN, okay? It doesn't show all of them, but they're connected to them, okay? And there's 7 bridges, okay? Bridge number 101, 102, 103, 04, 05, 06, and 07. You can see that bridge number 101 connect LAN A and LAN B, okay. Bridge number 107 connect LAN A and then E, okay. So there are more than one way to go, okay, from station 1 to station 5. Okay, station 1 is in LAN A and station 5 is in LAN E, right? So you can go from station 1 by using bridge number 101. And then use bridge number 104, okay, to LAN E and go to station 5. Or you can go directly, okay, from station 1 in LAN A using the bridge number 107 to bridge to LAN E and to station 5, okay. So have to make a decision on which bridge, okay, that you want to use. So this is kind of the routing that we have done before, but instead of the node, it's become a bridge, okay. Let's look at the routing strategies, okay. The first one is fixed routing. For fixed routing, the routes between each pair of a source and the destination lanes are fixed. So we can do like the least cost routing, like the Dijkstra or the Bellman-Ford, okay, to find the best route between a source and the destination. And after you find it already, you will not change it. Okay. For example, in this, as I was talking about, if you want to connect LAN A and LAN E, you should use bridge number 107 instead of 101 and 104. Okay. And if topology is changed, which means that you change the connection of the bridge, then you can change the route, okay. If not, you use always the same route, okay. The second one is a spanning tree routing, okay. In this case, you will have the bridge in the spanning tree routing has an empty routing table at first, okay. So for the fixed routing, you have the routing table, okay, after you are done with the algorithm, okay. So every bridge has a routing table. But for the spanning tree table, serenity routing, at first you have empty routing table for each of the bridge. And then we use flooding, okay, as we have talked about before. We use flooding algorithm, okay, to send frames to unknown destinations. So when we go to any bridge, okay, the bridge will send this frame, okay, to all of the link all of the LAN that is connected to it, okay, because this is flooding. Then the bridge will learn more and more about, not the above, about, okay, about the connection by using the backward learning algorithm, okay, and we will look at it from this example of the backward learning, okay. So you have LAN LAN 1, 2, 3, 4, and you have the bridge B1 and B2, okay, and you have station A to H, connected to all the lands. You see that when bridge B1 see a frame from land 2, okay, that has a source destination of station C, then it learns that land 2 can reach C, okay, and so it's put in the routing table that if you want to send to land to station C, okay, you should go to land 2, something like that, okay. So if you look at an example. Okay, so we have example here. Okay, so this is the same as what you see before. Now, if C want to send something, it will send something like this, okay? If C want to send to F, okay, C send to F. C send to F. So this is source and the destination address. Source address, destination address, okay? So C send to F. You go this way and go this way, right? So at first, the routing table in bridge 1 routing table is empty, right? This is bridge 2. Routing table is also empty. Okay. So when bridge 1 see this, okay, even though F is not in this land, okay, but at first it doesn't have anything in the routing table because so it has to use flooding. So you just send out to this land, okay. And this one also send out to this and to this land. Okay. Now, for the routing, okay, destination, okay, so when bridge B, B1, okay, see the packet look like this, C and F, and this is data, okay, so this is source and destination address. So it's know that C is a source address and coming this link, coming into the bridge this way, okay. So B know that if you want to go to station C, you can go to land 2. Okay, you understand? So if you go to because you receive a frame, okay, that have C as a source coming from this link, coming from land 2, it means that if you want to send a frame, okay, to station C, you have to go out to land 2 too. Now for bridge number 2, the destination and the land. Okay, so it's look at this the same. Okay, it's received from this link from land 2. Okay, the source with the destination source C and destination F. So the bridge knows that if it want to go to C, it have to go to land 2 again. Okay, so in this 2 routing tables you developed from the empty routing table, okay, to have some information. This frame, okay, we go this way and go this way. When it go to F, okay, this is correct, so you just go to F, make a copy, okay, but the other we just ignore them. Okay, next, suppose now D want to send to B, okay. D send to B. Okay, so this is source and destination. So D send out both ways. Okay, coming here, bridge B2 saw it, okay, D want to send to B. So if I want to go to D is a source address, right, coming from LAN 3. So next, if I want to go to D, I will go to LAN 3, okay, it will eventually go to D. Then bridge number 2, since it doesn't know where B is, okay, it have to send out this way and this way. Okay, go this way and go this way. Okay, this one go no B, doesn't matter. Okay, this one go. Okay, then bridge 1, see this one with the D and B, right? D and B. Okay, so source is D and the destination is B. So bridge number 1 know that if I want to go to destination D in the future, destination D, I have to go to LAN what? LAN 2. Okay, so it will go this way, and then it will send to this way. Okay, then B will make a copy, and then send along the line. Okay, so can you see how it developed the routing table? Okay, with the backward learning. Okay, again, if now C want to send, if E want to send to C, now you don't need this is source and destination, okay? E want to send to C, so it send, okay, along the way, like this. At B2 knows that, oh, go to C, go to LAN 2. So it will just send this one to LAN 2 and not to LAN 4, okay? So no flooding anymore. No use of flooding anymore. This one you have to use flooding because at first you don't know where it is. This one you have to use flooding. But in this case, you don't need to use flooding anymore because you know that go to C, you go to LAN 2. So you just go to LAN 2 and not go to LAN 4. Okay? And then when this one received, okay, with the destination of C, when it receive it, it will not go to LAN 1 because when it receive it, know that destination C is in LAN 2, right? So it received this one, it will not send out, okay? It knows that it have to stay in this link or this LAN, okay? I hope this is understandable. Now let's look at the problem with the flooding, okay? If there is a loop, a closed loop, okay, of bridges, there will be a problem with flooding, okay? So you have to make sure that there is no closed loop. Now let's see what is the problem, okay? Suppose you have bridge alpha and bridge beta, okay, connecting LAN X and LAN Y together. And suppose that station A want to send a frame to station B. So A send both ways, right, on the left and on the right. Since the bridge doesn't know where B is, okay, so the bridge will send out to all direction, okay, which is the flooding. But in this case, there is only one direction connecting the bridge alpha, okay, another direction, which is LAN Y. So bridge alpha sent to LAN Y. Bridge beta also receives the packet, doesn't know where station B is, also sent to LAN Y. Now, so now there are frames, okay, on LAN Y, okay, that are 2 frames, okay, that want to find station B. So one copy from bridge alpha, one copy from bridge beta. Now bridge beta look at the frame, okay, that the bridge alpha transmit, okay, so it's look at it, okay, it doesn't know where B is, so it's sent back to LAN X. Bridge alpha look at the frame, doesn't know where B is, okay, because everyone will see, okay, what is on the LAN, right, it's broadcasting. So bridge alpha look at the frame on LAN Y, okay, doesn't know where B is, it will send to LAN X, okay. So now it generate copies, okay, of the packet or of the frame, okay, indefinitely. Okay, so you will have problem as more and more frame will circulate in this loop, okay? So how to avoid this? You have to avoid the loop, okay, basically. So you have to avoid the loop. And how to avoid the loop, okay? You can use a spanning tree, okay, to avoid the loop. It's just basically like this, okay? So you have let's look at this, okay? As the land is the rectangular, okay? This one is represent land, and the line represent the bridge, okay? And if it's a solid line, represent the bridge that are used in the spanning tree, and or a part of the spanning tree. But if it's a dotted line, it's a bridge that is not used as a part of a spanning tree. So you can see that you have to avoid having a loop, right? So the solid line, okay, they will connect like this, okay? This is a tree, okay? They have a branch and they have a root, but no loop, okay? So the bridge that will make a loop, you just don't use it. It has to be a unique part, okay, between land A and land B and any other lands, okay? So if station A wants to send to an unknown destination, it will send in all directions, okay? And it will learn, okay? And also the frame will reach the destination because the spanning tree connect all of the lands inside, I mean, with the branch, okay? With the bridge, okay? So no problem, any frame will go to any of the destination even though it's unknown. But after you learn about that, okay, after the bridge, okay, learn about the source that, oh, coming this way with this source, so it's put in the routing table, so you learn with the backward learning. So after it update the routing table, okay, the flooding algorithm will be used less and less, okay, until there's no need, okay, to use flooding anymore because you will send to a known destination, okay, and there's no need to use flooding anymore. You send them directly. So so if land A want to send to something like on the bottom land, okay, just go that way directly, okay, after you have the routing table already. Next, we'll talk about chapter 11, okay, a little bit of chapter 11. Chapter 11 is devoted to Ethernet because Ethernet is the most popular LAN right now, okay. So the WLAN for WLAN, okay, most popular WLAN right now, okay. So this is based on the 802.3 standard. It's commonly called as the Ethernet, okay, with the E, with the capital E, not the internet, okay, Ethernet. So this one is used, originally it's used bus topology and the broadcast techniques, okay. The new high-speed Ethernet, okay, changed to use the switch-based techniques. The data rate supported by the Ethernet, okay, increased in terms of, in order of magnitudes, okay, from 10 megabit per second to 100 gigabit per second, okay. So very high data rate, and it will be higher and higher, okay. So this graph shows you that after the end of 2013, you can go to 100 gigabit per second, okay? About 20% will use the data, 20% of the data center, okay, will use the 100 gigabit per second. Anyway, let's look at let's look at the traditional internet first. The 802.3, okay, medium access control protocol use CSMACD techniques, which is, as I told you before, carrier sense multiple access with collision detection. Okay, so we use this up to 1 gigabit, okay, Ethernet. Okay, so we use this technique up to 1 gigabit Ethernet. So it's used in many current LANs, okay, but if you go up to 10 gigabit per second and higher, like 40, 100 gigabit per second, we will not use CSMA-CD anymore. Okay, we will change to switch base. Okay, now to understand the CSMA-CD techniques, okay, we will first look at the previous techniques. Okay, originally its contention is from the technique called Aloha. Then we have the CSMA, which is carrier sense multiple access, and then we go to CSMA-CD, which include the collision detection. Now, Aloha, as I told you before, it was originated in Hawaii, and so this is the greeting of Hawaii people. Okay. This one is for the packet radio networks. Okay. If you know the Hawaii island, they have many islands together. Okay. And so they want to communicate. Okay, between the island. So you have many islands here. Okay, and then you want to talk to each other, right? So you have like a base station. Okay, so you want to send data. Suppose this guy want to send data, so it's sent to all direction. Okay, so everyone receive a packet. Since at first, okay, not many people are sending, okay, and they may send just important information, short messages, okay, and not often, okay. So if this guy want to transmit, it just transmit directly. It doesn't care if anyone is transmitting or not, okay. So it just send out, and then it listen, okay, to the medium, okay, whether there is any collision. Okay, if there is a collision, it has to retransmit, right? But if there is no collision, then it's a successful sending. Okay, so very easy. If another guy, this one want to send, again, it's also just sent. Okay, and everyone will hear, okay, what is transmitting. There are two techniques of Aloha. Okay, the first one is unslotted Aloha, or we call pure Aloha. Another one is called slotted Aloha. Let's look at the first one, pure Aloha or unslotted Aloha. As this is the same as what I just told you, that is station transmit data at will. So whenever you want to send, just send, okay? And just observe any collision, whether it's occur or not. If it occurs, we wait for a random period of time, okay? Random time. Before trying to transmit again, okay? But collision occur when there are other stations, okay, sent at the same time. This is the simplest techniques, but the number of collisions increase rapidly, okay? If you have an increased load, which means that if more people want to transmit, okay, more data is transmitting, then the collision go up quickly, okay? And the maximum utilization of the medium is just about 18.4%. Let's look at an example. If you have only a little overlap, okay, between two stations, it's already a collision, okay. So if this guy sent almost done, okay, maybe 90% of the message already, but another guy start transmitting and it collapse, it collide with only 10%, okay. The whole thing is like fail, okay, fail transmission. So unslotted Aloha or pure Aloha, even though it's very simple, it's very low maximum low utilization, okay, of the medium. So that is another technique, which is a simple technique, but make it to be higher efficiency. So the maximum utilization is about 36.8%. This one we use slotted Aloha because most of the time that is overlap, it may overlap only just 5%, 10%, 20%, okay, not all of them. So in this case, it will divide the time in the medium into slot, okay, and then when it the station can send only at the beginning of the slot. If it come in between, if they want to transmit in between, it have to wait until the beginning of the next slot. So the collision will be collide for the whole slot or not collide at all, okay. but station can still send in any slot that it want to. It just have to wait until the beginning of the slot. So it have less collision because either no overlap at all or overlap completely. Okay, so efficiency is go up. So let's look at this. So if you have the time like this, okay, and you divide this one into slot. Okay, so if A want to transmit, if A come in at this time, okay, A cannot transmit, okay, because this is in the middle of the slot. A have to wait until the beginning of the next slot to transmit. So this is A data, okay, A packet, okay. Then if B come in at this time, B cannot transmit, okay, B has to wait until next slot. So B will send here. So there is no collision, right? Even though if you have unslotted or the peer aloha, if we start sending here, it will have a collision at the end of the A packet, right? But because you use slotted aloha, so B wait until the beginning of the next slot. So there is no collision. Now, if C come in, C want to send at the same, okay, the same in the same slot as B, okay. I mean, instead of starting here, okay, and it will start at the beginning of the next slot. So C send here. So the whole thing will collide, okay, collide for the whole slot. Then B come back again. B wait for a random time. B may come back here, wait, and then transmit here. Then C may come back later. Okay, C may come back here, and it will transmit here. So no collision anymore. So when it is collide, it will collide completely. When it's not collide, it will not collide completely. So there is no problem like just a little overlap as in the unslotted aloha. Okay. The next technique is called carrier sense multiple access, okay, or system A. This one use the propagation, use the fact, okay, that the propagation delay between stations is very, very small because the signal go very fast, okay, and the stations, they are close together. So if you compare the propagation delay between stations with the frame transmission time, you find that the frame transmission time is much longer than the propagation delay. So if you just wait a little bit, okay, and before you transmit a frame, you listen, okay, whether there is any station sending in the medium or not. Because when a station started to send, all of the other stations will know this almost immediately, okay? Because when like this station send, it goes both ways, right? Send the signal both ways, and the propagation delay is small. So in a very short time, okay, other station will know that there is something transmitting on the medium. Okay, so in this case, if you are the station and you are connected to the bus, okay, you just listen first, okay, whether there is any signal transmitting or not. If there is any signal transmitting, you have to wait until it's done, okay? We have two techniques about how to wait, which I will talk about. But if it's free, the medium is free, then you just send out, you can send out at that time. And we reduce a lot of probabilities of collision, okay? Now, so in this case, when the station want to send data, it will first listen to the medium, as I tell you before. This is called carrier sense, okay, sense the carrier in the medium, okay. And if the medium is busy, station will not transmit. So there is no collision. But if it seems available, okay, I use the seam because it may not actually be available, but someone maybe just start to send at the same time as you are sending, okay. But if no one is sending, when you listen, okay, it have a good chance, very high chance that no one is actually transmitting. So then it will transmit the data, okay, the collision can still occur, as I say, that it's not proof, because if you and another station just happen to send at almost the same time. So when you listen, it's free, the channel is free, but then just when you start to transmit, okay, it just happened that they are transmitted at almost the same time and then will collide. So if the collision occurs, the data will be retransmitted. As I say, okay, if you want to transmit at about the same time, you will have a problem. This is CSMA. Then they have another technique which is used in the Ethernet or CSMA CD. The collision detection, okay, at the end / CD at the end is to reduce the time of the collision, okay, because for the first case, the CSMA, when you transmit and if it's at about the same time, it will just keep colliding until the end of the packet, okay, or the frame. But if you use Ethernet or use CSMA CD, so after it's transmitting, not only that it listens to the medium before transmitting, it's also listen while it is transmitting. So if it's heard that there are some other signal, okay, collide with its signal, it will stop transmission immediately. So the duration of the collision will be short, much shorter than if you just allow it to collide for the whole frame, okay? So this one has a much higher efficiency. Okay, so this is what the difference, because CSMA is listen to before it transmits, CSMA CD is listen before it transmit and listen while it is transmitting. Okay, now this is the persistence, CSMA persistence and back off when the channel look busy, okay, when you check the channel and the channel is busy. So at first, okay, it's ready to transmit, okay, found that, listen to the channel is busy. There are actually 3 techniques, okay, to come back and transmit. The first one is called one persistent. There's one persistent, non-persistent, and P-persistent, okay? For the one persistent, okay, this one you transmit as soon as the channels go as idle, okay? So you wait, okay, you listen to the channel, you wait until the channel is available, it's free now, so you're transmitting at that time, okay. This is good if no other station is also waiting, okay. So if you are the one who are waiting, so you have high efficiency that at the end of the frame you can start transmitting. You still have the shortest wait. However, if another station, if suppose 2 stations coming in, and then channel is busy, so they are both waiting. So if you say at the end of the frame, when it's free, start sending, okay, both of them still send at the same time and you will collide, okay. For non-persistent, okay, you will transmit if it is idle, okay, if you have collision, then you back off, okay, both of you will back off. For the non-persistent, you transmit if idle, okay, and if you are busy, if you sense the channel is busy, then you wait for a random time, okay, and repeat the process. So you wait for a random time, you come back and listen again. So it have a lower chance, okay, of colliding with another station, okay. So if it's busy, you're not sending. You go out for random time, okay, and then you come back and then listen again, whether it's busy or not, okay. If it's idle, you transmit. If it's busy, then you go out for a random time again, maybe buy coffee or something, okay. So go out for a random time again, and then go back and check again, okay. And if there's collision, then you back off. P-persistent is just in between of the one persistence and the non-persistent, okay. So you transmit as soon as the channels go idle with a probability P. So it depends on what you are setting. Suppose P is like 0.5, so 50% that you transmit at the end of the frame that the channel is busy, okay, and 50% that you will not transmit. So it will reduce the chance of if there are many station, more than one station waiting, okay, to transmit. And if you are not sending, suppose 50% chance, okay, you are sent immediately, 50% chance you are not sending. Suppose you are not sending, then you wait for another time slot, and then send again with a probability of P, okay. So again, for the next time slot, 50% chance transmitting, 50% chance not transmitting. And if collision, you back off, okay. So this should be the one persistent, okay, not it one persistent strategy. And then non-persistent. And then P persistent, okay? So this is typo here. It should be one persistent. So, okay, what to do if station sends that the medium are busy? Okay, the three techniques: persistent, non-persistent, and P-persistent. Okay, so persistent is like you keep bugging it. Okay, keep sending until the medium is free, then you send immediately. Delay is not wrong. It's not long. The good thing is that delay is not long, but there may be many collisions. Okay. If more than one station wait, okay, for the medium to be free, then collision definitely. Non-persistent delay is longer, but not many collisions. Okay, because come back at the random time. When it come back, if another one starts sending already, then it will listen, or channel is busy again, it will go out again and waiting again. P-persistent again. It's just a compromise, okay, in between the two techniques. So this is the end of this video, and for the next video, we will start with the examples of the space-time diagram, okay, of the CSM-ACD, which is quite detailed. Okay, thank you.